Hello guys, I am Nurin.
Hi everyone, I am Nina. Polymer clay nanocomposite?
It is the polymers combined with layered silicates at the nanoscale to form nanocomposite. Besides, the composite in which one dimension of at least one component is in the nanometer size scale, less than 100 nanometer, is defined as nanocomposite material. Polymer nanocomposite emerged as one of the most promising developments in the area of flame retardancy, appearing to offer significant advantages over conventional formulations. For instance, polystyrene, polymethyl methacrylate, polypropylene, and polyethylene. Subsequently, it is applied in food packaging, flame retardant wall panels, textile fabrics, and also flame retardant doors. Moving on to the drawbacks and limitations, halogen-based flame retardants were used, and these materials were found to be effective for flame retardation. However, these materials were inhibited due to their associated environmental pollution. Other than that, metal hydroxide have been used as flame retardants additives, but their high effective loading was attributed to poor dispersion and drawbacks in mechanical properties of polymer composites. On the other hand, the use of clays greatly limits the class of miscible polymers only to hydrophilic ones, mainly polyethylene oxide and polyvinyl alcohol. Clay usually contributes to stability by acting as heat insulator and as mass transport barrier to oxygen and the volatiles generated during polymers degradation. The improvement in thermal stability may be limited since by the clay itself or the decomposition products of the organic modifier which can catalyze the degradation of the polymer matrix.
Next, the properties of the material. First, lightweight and improved thermal stability. Second, clay particles play a catalytic role on the char-forming reaction. Third, the layered silicate nanocomposites incorporation of clay enhance the thermal stability. So, the last properties are high modulus and also increased solvent resistance. Now, let's proceed with material forming process. Type 1 process is in situ template synthesis or so-called sol-gel technique. In this process, it could promote the dispersion of the layer of clay in one-step process. Next, sol-gel technique need high temperature that can cause the polymer decomposition. And in this process, the aggregation occurred due to growth of clay layers. Type 2 forming process is solvent-assisted blending. This process is difficult to use in industry due to large amounts of solvents are used during synthesis. Last but not least, this process is environmentally disadvantageous. For type 3 forming process is polymerization technique. Polymerization techniques widely used to prepare polymer layered clay nanocomposites. The clay is dispersed in the monomer and polymerization of the monomer is carried out. This forming process can be delaminated followed by a polymerization step. Last but not least, this technique can be exfoliated during polymerization by triggering polymer chain growth within clay galleries. And for the last type of forming process is called melt blending. This process is most utilized for the preparation of nanocomposites, and it is suitable for large-scale production. Lastly, melt blending utilizes the existing conventional polymer processing equipment like extrusion and also roll mixing. Next, the actions to overcome limitation and drawbacks. So first, increasing the clay loading, the strength and modulus of PE clay composite increase while the notch impact strength decreases. Second, the use of other various nanomaterials as flame retardant fillers such as organoclay, metal oxide nanoparticles, carbon nanotubes, and graphene sheets. These materials improve the mechanical and flame-resistant properties of polymer nanocomposites. Third, the use of combination of charring agent, blowing agent, and acid source termed as intumescent flame retardant achieve good flame retardancy of polymer composites and low toxic gas emission. Fourth, to overcome the class of polymer limitation restriction, the silicate surface is modified by exchanging the cation initially present in the interlayer with organic cationic surfactants, mainly including primary, secondary, tertiary, and quaternary alkyl ammonium or alkyl phosphonium. So for the next actions, various aluminosilicates have been used as flame retardant fillers such as montmorillonites, halloysite nanotubes, and zeolites. These materials were used alone and in conjunction with other conventional flame retardant materials as synergistic fillers. Last but not least, phosphorus containing flame retardants has been used, which was based on condensed phase action through char forming effect.